Imagine a world without it. Your smartphone, the polyester in your clothes, the aspirin in your medicine cabinet, and the fuel that powered the plane on your last vacation, they all share a single, dark, viscous origin story. We call it black gold. But to the engineers standing on a vibrating steel deck in the middle of the North Sea, it's just crude. Extracting oil isn't as simple as sticking a straw into the ground and watching the money flow. It is a high-stakes, multi-billion-dollar game of chess played against the Earth's crust, thousands of feet below the waterline. The invisible reservoir. Before a single drill bit touches the dirt, we have to find it. Forget the cartoonish idea of giant underground lakes of oil. In reality, oil is trapped inside the microscopic pores of sedimentary rock. Think of it like a giant, oil-soaked stone sponge buried under miles of pressurized sediment. To find these sponges, geologists use seismic surveying. They send shock waves into the ground using compressed air guns or thumper trucks and listen to the echoes that bounce back. By timing these echoes, supercomputers build a 3D map of the subterranean world. But even with the best tech, you don't truly know what's down there until you spud the well. Seeding the beast. The process begins with an intense mechanical ballet. If you were standing on the deck of a deep-water rig, you'd hear a symphony of shouted commands and the rhythmic groan of heavy steel. Watch your hands. Almost there. Guide it in. All right, it's seated. The first step is installing the conductor pipe. This is a massive steel tube, sometimes 36 inches in diameter, that acts as the foundation for the entire well. Engineers lower it slowly, monitoring the alignment on every section to ensure it's perfectly vertical. Once it's pinned and secured, the riser connection points are engaged. These are the umbilical cords of the oil world, connecting the rig on the surface to the wellhead on the seafloor. The drill string, a 2-mile needle. Once the foundation is set, it's time for the drill string. Imagine a hollow steel pipe, only about 5 to 9 inches wide but stretching for miles. At the very end sits the drill bit, usually a masterpiece of engineering studded with industrial diamonds or tungsten carbide teeth. As the rotary table on the rig floor begins to spin, the drill bit eats into the rock. But you can't just drill a dry hole. To keep the bit cool and prevent the well from collapsing, engineers pump drilling mud down the center of the pipe. This isn't backyard mud, it's a high-tech weighted fluid that carries rock chips back to the surface and, most importantly, provides hydrostatic pressure to keep the oil from exploding upward prematurely. The torque game. Down in the hole, things get violent. The friction is immense. On the rig floor, technicians watch the monitors like hawks. Torque is fluctuating wildly. We need to adjust the weight on bit. If the bit bites too hard into a layer of dense rock, the torque spikes. If the driller doesn't ease off the pressure, that multi-million-dollar drill string could snap like a toothpick, leaving miles of steel trapped in the earth. It's a delicate balance of RPMs and downward force. They gradually increase speed as they cross density thresholds, moving from soft shale into hard limestone, constantly adjusting the weight to maintain a steady flow of progress. The blowout preventer. As the drill approaches the reservoir, the pressure climbs fast. You are essentially poking a hole into a high-pressure soda bottle that's been shaken for 50 million years. To prevent a blowout, a catastrophic eruption of oil and gas, engineers install a blowout preventer. This is a massive stack of valves, sometimes weighing 300 tons, sitting on the seafloor. It acts as the ultimate emergency brake. If the pressure in the well spikes beyond the mud's ability to hold it back, the BOP can instantly shear through the drill pipe and seal the well shut with thousands of pounds of hydraulic force. Casing and cementing. You don't just drill a hole and leave it. As the bit goes deeper, the crew has to case the well. They pull the drill string out and slide in a steel casing pipe. Then they pump cement down the middle. This cement flows out the bottom and back up the sides, bonding the steel pipe to the rock. Ultrasonic scan on the weld joints confirms integrity. All systems green. This creates a permanent sealed conduit. It protects the surrounding groundwater from contamination and ensures that the only place the oil can go is up the pipe. Without a perfect cement job, the pressure from the earth would simply crush the well like a soda can. Perforation, the final shot. Once the well reaches the target depth and the casing is cemented, the oil is still trapped behind that steel and concrete. To get it out, the crew uses a perforation gun. This tool is lowered to the depth of the oil-bearing rock and fired. It uses shaped charges, the same technology used in anti-tank missiles, to blast tiny holes through the steel casing and deep into the rock. Suddenly, the sponge is open. The pressure that has been trapped for eons finally has an exit strategy. The crude begins to seep through those holes, into the wellbore, and starts its long journey to the surface. Initiating the flow. Back on the bridge, the tension is palpable. Initiating flow sequence. Valve adjusted. Check the flow rate on line 2. At first, the natural pressure of the reservoir is often enough to push the oil to the surface. This is known as primary recovery. But the flow has to be managed. If the pressure is too high, it can damage the equipment. If it's too low, the oil won't move. Technicians monitor the manifold, maintaining a steady 40 megapascals of pressure to ensure the seals hold. Pressure stabilizing at 40, cap is holding steady, transfer initiated. The crude finally reaches the surface, where it is separated from natural gas and water, then diverted into massive storage tanks or directly into subsea pipelines. The well is officially live, but the work is just beginning. The natural pressure of the reservoir can only do so much. Eventually, that soda bottle loses its fizz. When the oil stops flowing on its own, engineers move into secondary recovery. Think of it like trying to get the last bit of toothpaste out of the tube by squeezing from the bottom. If water doesn't work, they might use enhanced oil recovery, EOR. This involves injecting steam to thin out the thick, heavy crude or using CO2 to change the chemical properties of the oil so it slides through the rock pores more easily. It's a constant battle against friction and physics. The separation ballet. What comes out of the ground isn't just pure gasoline. It's a messy cocktail of crude oil, salty produced water, and natural gas. Before it can go anywhere, it hits the separator. Check the flow rate on line 2. Flow stabilizing. System check complete. Inside these massive horizontal tanks, gravity does the work. The gas rises to the top, the oil settles in the middle, and the heavy salt water sinks to the bottom. Each stream is siphoned off. The gas is often compressed and sent via pipeline. The water is treated and pumped back into the ground to maintain pressure, and the oil, the black gold, is finally ready for transport. The journey to the refinery. Whether it's loaded onto a VLCC, very large crude carrier, or pushed through a transcontinental pipeline, the crude's journey is far from over. It's still just a raw ingredient. To turn it into something useful, it has to be cracked. At the refinery, the oil is heated in a fractionating column. Since different components of oil, like butane, gasoline, kerosene, and bitumen, all have different boiling points, they distill at different heights in the tower. The digital oil field. In 2026, the roughneck with a wrench is being joined by the data scientist with an algorithm. Modern rigs are covered in thousands of sensors measuring everything from vibration to chemical composition in real time. Diagnostics are clear. All systems green. Maintaining course and speed. Using digital twins, engineers can simulate a drill's path through a specific rock formation before the bit even spins. This allows them to avoid trouble zones like high-pressure gas pockets or unstable shale that could cause a blowout. We are moving toward a world where the rig is a giant, autonomous robot, capable of making micro-adjustments to the drill speed and mud weight faster than any human operator could react. Closing the loop. The final stage of the extraction story isn't the oil leaving the rig, it's the rig leaving the ocean. When a well is tapped out, it must be plugged and abandoned, P&A. This is a massive environmental undertaking. Engineers pump specialized cement plugs into the wellbore to seal it forever, ensuring no oil or gas can ever leak into the ocean. The riser is disconnected, the subsea wellhead is removed, and the site is returned to the seabed. Finalizing the sequence check on the riser controls. Systems are fully integrated. We are ready for decommissioning. It is a cycle that takes decades and costs billions, fueled by the world's insatiable hunger for energy. From the first seismic shockwave to the final cement plug, oil extraction is arguably the most complex engineering feat humans have ever mastered. But here's the thing about the modern oil field. It's now a high-tech, subsea factory. In the most advanced fields of 2026, we've moved the entire operation from the surface down to the ocean floor. Imagine massive, robotic processing plants sitting 2 miles underwater, operating in total darkness and crushing pressure, separating oil from gas before it ever reaches a pipe. This is the subsea tieback revolution. By placing the separation equipment directly on the wellhead, engineers can pump the crude over much longer distances, reaching satellite pockets of oil that were previously too small or too deep to be profitable. It's like having a localized vacuum system for the Earth's crust. If a vibration sensor on a pump thousands of feet below the waves starts to spike, the AI detects the pattern before the part actually fails. This level of oversight is what allows the industry to push into frontier regions, the ultra-deep waters of the Atlantic or the frozen shelf of the Arctic. We are no longer just drilling for oil. We are managing a global, interconnected nervous system of energy extraction. As we move toward a diversified energy future, the role of crude is shifting. It's becoming less about the fuel in our tanks and more about the feedstock for the high-tech materials of tomorrow, the carbon fibers, the medical-grade polymers, and the advanced lubricants that keep our renewable infrastructure spinning. The ballet of heat, pressure, and precision continues, not just to power the world, but to build it.